Hello, welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video we continue looking at recursion, and in particular recursion where we have a function call itself multiple times. And in this video we're going to look at one of my favorite examples of this type of a recursive problem, and that is the example of mazes. And so we're going to use a fairly simple model for a maze. We're going to treat our maze as just a two-dimensional array like this, where every box can either be someplace that you can pass, these would be the white boxes, or someplace that you can't pass, and this would be the black boxes. And so the idea is I want to ask, given a particular location, how many steps is it to get to the end of the maze? And the question is, how can we write an algorithm that will solve this problem for us? So there are lots of ways that you can do this, but of course a simple loop is not one of the answers, because when you're going through this maze, so a loop would work fine from here. You just say, okay, well I have to go here, I have to go here, I have to go here, but now you have two choices. You can go that direction or you can go that direction. And of course from a location like this there are four directions that you can go. So this is the challenge of solving this, and there are multiple ways of doing this. We're going to look at, of course, the example solution that uses recursion, and this problem lends itself very, very nicely to being solved recursively, which is obviously why I use it as an example. And so just like with our other versions of recursion, we're going to need to have some type of base case or base cases. In this case we'll have at least two base cases, and then we also need the recursive case. And so the question is, if you're at some particular location, no idea what that just did. Okay, that was weird. It just zoomed in on that one block. If you're at some location here, and I want to know how many steps is it from here to the exit. Maybe we'll say the exit is down in this location, or maybe it's not. Maybe this is the exit. I don't know. To answer this question is in and of itself a hard problem. But go back to what we were talking about with the Fibonacci numbers. I said, assume that I have some type of a magical oracle that can give me the answer for other problems they're theoretically closer to the solution. And so in this case, I'm going to say, well, I don't know how many it is from here, but what if I could ask some magical oracle how many steps it was from here, from here, from here, and from here. So if I could ask how many steps there were from these three different directions, then how far would it be from this particular location? Now, if you ignore this maze, and I'm just going to assign some somewhat random numbers to this. Let's say that from here it came out that there were 10 steps, and from here there were 5, and from here it was 7, and from here it was 19. Okay. And then the question comes, well, if those were the number of steps that our oracle told us you had to take to get there from those four locations, how many would it be from right here on the shortest path? Because that's what we're interested in. We're actually going to write an algorithm that solves just the length of the shortest path. And of course that algorithm can be applied to actually find the shortest path if you want, but right now we're just going to make it so it returns a simple integer for the length of that path. Well, if you want the shortest path, turns out the answer is that you should obviously go that way. And so it's going to take you one step to get here, and then from here our oracle told us it was 5. So that means that clearly the distance from this location would be 6. Okay. So if we had some magical oracle that could give us these numbers, we could definitely find this. And what we do is we can combine them, and we combine them by taking the minimum of the four values, and then we have to add 1 to that minimum. Okay. And so it turns out there are lots of different questions you can ask about mazes, and when you ask different types of questions, you combine these four return values in different ways, and you also have different base cases that work out well with it. Oh, hey, that's interesting. While I was hitting undo, I managed to change the color of two of my maze squares. There we go. Okay. So that's our general approach in terms of a diagram and talking it through. Now we need to translate that into code. So if I write a maze.scala, the first thing that I want to put into here is to declare my maze, and I'm going to use an array of integers in here. And to start with 4, 5, 6, 7, 8, 9, 10. I'm going to make this a 10 by 10 array of arrays. So 2, 3, 4, 5, 6, 7, 8, 9, 10. This is actually a little bit bigger than what I have in the figure. This figure here is 10 across, but it only fits nicely 8 vertically. So this will be a little bit bigger, and I'm going to use zeros to represent the open spaces where you can go, and I'll use negative ones to represent the closed spaces where you can't go. And we can produce something that is actually pretty similar to the maze that I have over on the other side. That'll work nicely there, and this is a little bit different, but not too much so. Okay, so that makes a reasonably nice 10 by 10 maze that we can play around with. And I want to find the length of the shortest path. Okay, now what information do we need here? Well, I'm going to pass in the maze. Technically the maze is declared above this and it's global, so I don't have to, but it makes me feel better to pass in the maze. What else do you need? Well, I'm asking for the shortest path from a particular location, so I need to know where I am. So I'm going to pass in an X and a Y location in the maze, and then I'm also going to pass in the location of the destination. Where is our finish point? So I'll call this EX and EY for the end X and the end Y, and this function is just going to return an int. Now, part of you might say, well, but an int is not actually the path, this is just giving us the length of the path. That is definitely true. Part of the reason for that is because it turns out that there can be ambiguity on the actual shortest path. It could be that there is more than one path of the same length, and then we'd have to decide how we want to resolve that ambiguity and whatnot. But if you only find the length of the shortest path, that's non-ambiguous. All shortest paths have the same length. And you can use this if you wanted to find your way kind of out, if you were so inclined. Okay, so how can we make this work? Well, so we said earlier that we need to have, it's a recursive function, we need to have base cases. Okay, so what are our base cases? Well, one base case, the easy one to see, is if you get to the end. Okay, so if your XY location is the end XY location, how many steps does it take to get to the end of the maze from the end of the maze? 0. The next base case is a little bit less obvious, and in some ways this base case is going to be there because of how I like to structure this. When you have things that are situations that can't happen in your recursion, just realize that that makes it more like I had a dead end up there on the other one. If you have situations where you're not allowed to go there, you can either check for it on multiple recursive calls, or a lot of times you can check for it at the beginning of as soon as you enter the recursive call down underneath. And so I'm going to take that latter one because it generally simplifies the code dramatically to only have one conditional check at the top of the function as opposed to having multiple, in this case 4 different recursive checks. So what are the situations that kind of should not arise? Well, one is, what if you happen to walk into the middle of a wall? That's not an allowed position, and so we need to return something that says that's invalid. There's also the possibility of what happens if you walk outside of the bounds of the array. So if you go all the way off to the left or all the way off to the right or the top or the bottom, well, those are also not allowed. So I'm going to put those all in one situation here, one condition here. So if x is less than 0 or x is greater than maze.length, and this should be greater than or equal to, or y is less than 0 or y is greater than or equal to maze sub x dot length, or maze sub x sub y is less than 0. Okay, because that's inside of a wall. So first we check the out of bounds, and then we check for the wall. The ordering here matters because if x or y are out of bounds and we try to do this first, our code crashes. Well, in this situation, what should we give you back? We have to give you back a number that definitely isn't the answer. And a lot of students are tempted to put -1 here. We're not going to do that, though. We're actually going to return a billion. Okay? We need a big number. Another thing is some people wind up being, so not -1 or int dot max value. And when I write the next case, I'll come back to that and we can talk about why I don't make it equal to either one of those. So this is our recursive case here. We're not at the finish, we're not out of bounds, and we're not inside of a wall. Okay, so then what should we do? Well, as we talked about earlier, we need to use our magical oracle to find the distances in the 4 directions. And of course the magical oracle is this function itself. Okay, so we're going to call shortest path on the same maze once with an x greater than that's been incremented by 1. So this would be off to the right, the same ex and the same ey. We're also going to call it with going to the left, so x decremented by 1. We're going to call it down, and we're going to call it up. Okay, so these are 4 recursive calls, and then the question is, how do we put them together? Well, I want the smallest of these 4, and so you could use a whole bunch of ifs and temporaries and stuff, but remember that Scala allows you to use min between integers in an infix notation. Now really this is short for 5.min of 7, but it's a very helpful way to get the smallest of a bunch of numbers. So 5, min 7, min 9, min 3, min 4 gives me back 3 because that is the minimum of those different numbers. So I can do the same thing here. Min, min, min. I don't put 1 at the end. This is just like pluses. If I did 5 plus 7 plus 9 plus 3 plus 4, you don't expect to have a plus there at the end, just like I don't have a min here at the end, just like I don't have a min here at the end either. Okay? And I need to add 1 to this. Now, addition is a higher precedence than min, so I need to put all of these things in parentheses and then say plus 1. Now, let's go back to why I don't use -1 or int.maxValue. I don't use -1 because I'm taking the min. Okay? And of course, if landing in a wall returns -1, -1 is going to be shorter than any real path, and therefore it will win out. So that's the problem there. Now, of course, I could make it so that it has ifs around it and it checks for -1s and it doesn't accept -1s, but why? Okay, why should I go through all that extra effort when I can just use the min as an operator and I just have to return a big number? Okay. But of course there are bigger numbers. Now, it turns out that a billion is much larger than any real answer to this maze. Why not use int.maxValue? Occasionally, students are tempted to do this. Well, to answer that, so there's int.maxValue. It's a bigger number. It's a little over 2 billion. But note what happens if you add 1 to it. Well, then it happens to become int.minValue. Okay, so remember, this is that whole way in which binary numbers are represented inside of the machine. This isn't necessarily specific to Scala. This is how they are represented as 32-bit numbers inside of the machine. And once you go above the max value by 1, you wrap all the bits around and it becomes the minimum value. So I don't want to return the max value, because if I did this, well, then if these were all maximum values, when I would add 1 to it, then boom, that would become the minimum value, and all of a sudden that would seem like a great option. So I definitely don't want to do that either. So a billion is a nice compromise in this case. We are not going to make any mazes that are big enough to take a billion steps to solve. So let's try this. See what happens. Well, first, I guess I run this. We'll see if it compiles, see if I have any typos in there. Well, I haven't made it do anything. Hey, no typos. Okay, so it compiles. But now I need to actually call it. So I'm going to call it with the maze that we drew above. I'm going to start at 0, 0, and I want my endpoint to be 9, 9. So I am starting up in this corner, and my endpoint is down in that corner. Okay? And this should give us back, at least our goal is to make it so this tells us how many steps it takes to get through the maze from there to there. And when I run this, so somehow I erased my 9. Let's make this just a little bit bigger so you can see the whole code all at once. And boom, oh my gosh, it exploded. There was a runtime error. What happened? It's all line 18 called line 19, which called line 18, which called line 19, which called line 18, which called line 19. Boom, boom, all the way through. This was a Stack Overflow. I can't even get to the top. Okay? This was recursion that just kept going and going and going. So what happened here? Well, if we pull up our big diagram, what's happening here is that I'm, for example, on this square, and then it recursively calls it on this square, which recursively calls it on this square, and this square, and this square, and this square, and this square. And it's going back and forth and back and forth. And of course, no human would ever do this. They wouldn't sit there and step back and forth between two squares. But this isn't a human. This is a computer, and that's actually what we told it to do. Note that if you don't have walls around, if you can do it, you're supposed to go to x plus 1, and then after that tries x plus 1, it's supposed to go to x minus 1. And so it's possible to just alternate between these two calls, and that's exactly what's happening here. This is line 18, this is line 19, and so it takes a step to the right, and then from that step to the right, it takes a step back to the left, to the right, to the left, to the right, to the left, to the right, to the left. Clearly, we have to do something to prevent this. This is not acceptable. So the way that we prevent it is we somehow have to leave a record of where we've been. And I like to refer to these, to what we're going to do here is dropping breadcrumbs. Anyone familiar with Western fairy tales is familiar with the tale of Hansel and Gretel. And they drop breadcrumbs to mark their path. In the fairy tale, it's not a good idea because birds eat the breadcrumbs. There are no birds in the computer, though, so we will be perfectly happy dropping breadcrumbs in here. And if they wind up being eaten by birds in your computer, well, you have bigger problems. So what I'm going to do is I'm going to drop down at the location that we're at a -2 before I do this. So note that I say that anything that's less than a 0 is considered out of bounds. So now if I take a step to the right, when I take a step back to the left, it will hit this -2 and the recursion will terminate. And so I don't go left, right, left, right, left, right, left. I just go step to the right, step back to the left, return, and then go on with my recursion. However, I also have to pick these up. I can't just leave them out there. And the reason I have to pick them up is because if I don't pick them up, I might not find the shortest path. Imagine the situation where our first path the computer went all the way down and around and then up to here, and then it went and found the exit. Okay. If it doesn't pick up its breadcrumbs from that as the stack pops back out, when it comes back later and it tries this path, it will hit this square, it will see the breadcrumb that's already there, and it will determine that that is not viable. Okay, so we have to pick up the breadcrumbs, otherwise we will discount options which might actually be shortest alternatives. So we drop the breadcrumb, we pick it up. The only problem now is that now this isn't our return value. So I am going to introduce a variable for that and make sure we return that at the end. And there we go. This says 30. Well, interesting question. Does it take 30 steps to get out of this maze? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Yes, indeed it does. Okay, so we have a working function here. We'll come back next time. We will animate this so that you can actually see the algorithm working, and hopefully that will help you to understand it. And then we'll also look at the shortcomings of it and see if there's any way that we can